All right, good afternoon, everyone. We'll cover one last remaining slide in BJT fundamentals, and then we'll look into a transistor amplifier operation. Anyone have any questions before I begin? Okay. All right, let's go to the class notebook. So a few terms in here that we will cover. All right, junction breakdown voltage, base transit time, capacitance, beta cutoff frequency, and transconductance. Let's see. Okay, so if you remember the beginning of lab 7, we performed a small procedure to determine the terminals of our BJT. And that's what you're talking about in junction breakdown voltages. Um, we have two PN junctions, right? And so if we reverse bias either one of those junctions, whether it's a base emitter or a base collector, at some point it's going to break down. But the emitter is so heavily doped that it has Zener-like characteristics. Okay, so if you reverse bias a base emitter junction, then the breakdown characteristics or the reverse breakdown characteristics follow a Zener diode pattern. Okay, it breaks down within less than 10 volts. And this is what we observed. This breakdown voltage or reverse voltage, whatever you want to call it, is typically less than 10 volts. How many of you performed this procedure? At least in my lab, we did. I don't know the others. All right. So do you all recall what voltage it broke down approximately? So approximately 9 volts or so. So this is the base emitter junction. And then this is the base collector junction. The base collector junction will also break down, but not for at least tens of volts. Okay. So the characteristics would be kind of like just IS, reverse saturation current, if any at all, and then break down at some far voltage. And this VB is typically hundreds of volts. Hundreds of volts. And that is what allowed us to actually perform that small procedure to determine the terminals. Okay. Does that make sense to everyone? Okay. All right, base transit time. From the fundamental operation of a BJT, we know that the emitter is so called because it emits, that is the structure where the charge carriers are generated and emitted, right? So NPN transistor, emitter is N-type, generates electrons, not generate, sorry. You have large number of free electrons and they start moving from the emitter, cross over into the base, and from the base, they go into the collector. So there is a parameter known as the transit time, which basically tells us how long it takes for the emitter, for the charge carriers to cross from the emitter and arrive at the collector. Okay. This charge transfer or movement of electrons and holes does not take place in an instant. It requires a finite amount of time. And so that is known as the base transit time. Transits from the emitter to the base and from the base to the collector. Okay, so how long it takes for it to transit through the base. And it's noted by tau f. So the transit time is noted by tau f. And tau f can be given by the equation WB square, obviously because it needs to traverse the base times 2VT times mu n, where WB is the width of the base region. So base width, VT is the thermal voltage, and mu n is the mobility of the electron. Okay, carrier mobility. This is true for an NPN transistor. For a PNP, it's the same equation, but mu n is replaced with mu p. Mobility of holes. Okay, mobility of holes. If you recall from chapter 2, chapters 1, 2, and 3, holes are localized in the structure, meaning they can only go from available spots to available spots, whereas electrons are free to move around anywhere in the lattice structure. Mobility of electrons is 2.5 to 3 times that of mobility of holes. So devices where the primary carriers are electrons would tend to be much faster. In case of NPN versus PNP, primary carriers in NPN transistors are electrons. So for a given specific geometric shape and specific doping profile, apples to apples comparison, the same design and doping profile of an NPN versus PNP, an NPN transistor would be faster than a PNP transistor. Okay. With advances in design, of course, we can create, or we are able to create PNP transistors that are just as fast and capable as NPN. Okay. But that's how carrier mobility affects the speed of devices. Okay. Obviously, if it takes a finite amount of time for the electrons and holes to traverse and respond to external stimulus, that places a cap on the operating frequency of these devices, right? That's why there's a cap limit on frequency. That's why we have high frequency devices for specialized applications made from different materials. Okay, for silicon, typically that frequency is less than or equal to 1 over 2 pi tau f. 1 over 2 pi tau f. Okay, any questions? Where? Oh, holes. Holes and electrons. Mu n and mu p. Okay, let's move through the next three quickly. There is diffusion capacitance. Diffusion capacitance is basically where? Okay. It's associated with the charge that is stored in the emitter and the base region. Okay. So since the charges are actually moving through the junctions, the charge is actually stored in the base region before it goes over to the collector. And so the stored charge can be modeled as a capacitance. When the input voltage VBE changes, the charge changes, and hence, again, it can be modeled as a capacitance. CD, diffusion capacitance, can be given by the collector current IC or VT times tau F. Okay, tau. Then there is transconductance and beta cutoff frequency. Beta cutoff frequency, transconductance is how the input voltage is transferred to the output current. So it's basically a ratio of delta IC to delta VBE. So GM, transconductance, to IC or delta VBE for a fixed Q point. Okay, for a fixed Q point. And then beta cutoff frequency is, well, let's give it a pause. I'll wait for you all to catch up. Okay. All right. So we know about beta, right? Beta is the forward, or there's beta F and beta R. Beta F, the forward current gain, we specify as a single number. And we assume that it would be the same for most range of operations, but that is not true. It is frequency dependent, and there's an upper limit on the beta frequency. On the beta value. As the frequency increases, the beta remains constant, but there comes a time where it starts to slope downwards, meaning the beta of the transistor starts decreasing with increasing in the input frequency. Okay. And so there comes a point where we describe a cutoff for the beta that is known as the beta cutoff frequency FB. Okay. So if you model the value of beta as a function of frequency, let's do this. And so frequency in hertz, beta values on the y-axis. So beta as a function of frequency remains near constant for a long period of time. But once, that's probably not as sharp a cutoff, but it suffices for us. This is somewhere around 100 megahertz or so. Right, beta starts decreasing. That's FT. And we can define the function of beta as a function of frequency by this equation. Beta as a function of frequency can be given by the forward current gain beta F divided by 1 plus F over FB, which is that cutoff frequency. If you remember studying filters, or transfer functions for filters. I think what, 211, 212. High pass, I'm sorry, low pass filters. Ring any bells? Yep, yep, 228 too, yeah. Similar form. So the beta cutoff frequency FB is FT, which is the unity gain frequency divided by beta F. Unity gain frequency, as the name suggests, is the frequency where the gain is 1 or has a value of 1. Okay. All right, 330. Okay. Do you have a question? Okay. Let's go into some amplifiers. I wanted to explain the working of the amplifier since we performed those experiments and see or showed students how you can use load line analysis to explain the operation of a common emitter amplifier. Okay. Let's see. Okay, so everybody is by now, I'm assuming, familiar with the common emitter. Okay, there it goes, the rooster. Somebody on Zoom, please send a message. Okay, so as I was saying, everybody hopefully by now is familiar with the setup of a common emitter amplifier. This is not a voltage divider bias. This is simply the fixed bias where you have a collector resistor and a base resistor. Common emitter configuration. Emitter is common to the input and the output side. Our biasing voltages are VBB and VCC. We have a single reference point for all quantities right at the bottom. That's all it means. Doesn't mean that's the actual ground. And then we apply AC input at the base, or the V in of T is injected in series with the DC biasing. So single reference point, right? Sometimes we might have a emitter resistor in there, which would be known as the emitter bias. And then if you have two base resistors, that would be a voltage divider bias. So the DC voltages, what do? DC voltages are setting up the Q point. They are setting up the bias. And if you want this to work as an amplifier, that bias must set the Q point to operate in the active region. So the DC voltages, which is VCC and VBB, they are known as biasing voltages, and they, let me move this. These biasing voltages are going to fix the operating point in the middle of the active region. So Q point is fixed in the active region. If it's in cutoff or saturation, then we are using it for digital or switching. Okay. V in of T is sent into the base, and it's typically very small. Hence, any analysis that we perform with small signals is known as small signal analysis. Okay. So what the amplifier does is it takes, let's see, where. Okay. All right. So what an amplifier does is it takes the DC energy And let's say we are applying, doesn't matter what kind of DC we are applying. Let's say this DC has a value of anywhere between 15 to 30 volts. Okay, anywhere between 15 to 30 volts. This is T, this is value of the voltage. That's the DC biasing voltages. And then you have a small, very small AC signal, sometimes in the millivolt range. Okay, so this AC signal could be very small. And the analysis of a circuit or the response of a circuit to a very small input signal is known as small signal analysis. Okay, small signal analysis. So you can have large signal and small signal analysis. So far, so good. The total, yes, go ahead. In the question being asked is that DC representing both the DC sources. The answer is no. This is just a random, the random explanation for what actually happens inside an amplifier. So we have a AC signal that's applied as the input, and then what the amplifier does is that it takes energy from the DC sources and gives it the shape of this AC waveform. And so the output, what we have is this. So the answer to your question would be that no, it doesn't represent both. It's just representing whatever biasing is on the output side of the circuit. In this case, in this transistor amplifier, the output voltage or the output DC bias is VCC. So it would represent just VCC. The common emitter voltage divider bias that we used, it had a single VCC. So only single supply. So it didn't actually matter. Anyway, so the point still remains that we get an amplified version or a replica of that input signal. Okay. The energy to amplify a signal does not come from thin air. It must be supplied. It must be supplied in the form of biasing voltages. Okay, very critical point for students to understand. The energy to amplify any signal does not come from thin air. If an op amp has a gain of 100, we can't send in 1 volt and expect 100 volts at the output. Okay, that's not the way amplification works. The energy to amplify any signal comes from the DC biasing voltages. So obviously there's an upper limit on how much we can amplify a signal. If our DC biasing voltage is only 10 volts, we cannot expect an output greater than 10 volts, right? If it's 15 volts, cannot be greater than 15. Okay, so the voltages and the currents at any point in the circuit, VB, is a result of both AC as well as DC. Okay, AC as well as DC. So this is lowercase v with a uppercase subscript, which means it has both AC as well as DC. Lowercase is used for AC, uppercase, capital letters is used for DC. And when it's a mix of both, it means it has both quantities. When you perform analyses of these kind of circuits, we separate out the DC and the AC analysis, and that comes later on in this chapter. Okay. V out is equal to VCE, and VCE is the sum of both the DC as well as the AC. All right. So then let's look at the operation. Let's see how we can analyze this. And we'll perform load line analysis on this. Okay. All right. Let's get to it. So here's a common emitter amplifier. The input characteristics are shown to us. The output characteristics are also shown to us. We can use the load line analysis to explain how this amplifier works. Okay. First thing we can do is we can apply KVL on both the input and the output side to generate equations and plot our load lines. So let's apply KVL on the input side first. And we have 4 voltages minus V in of T, the AC input voltage, plus the base resistor voltage VRB, plus VBE, and minus VBB. Sum up to 0. I can write an expression V in of T plus VBB is equal to IB times RB plus VBE. If you're trying to solve this kind of circuit, well, V in of T would be given to us. The biasing voltage VBB would be given to us. The resistor voltages would also be, the resistor values would also be given to us, right? But right now we want to plot the load line. So if you wish to plot the load line, we have this equation. We are going to set IB and VB is equal to 0 to find the intersection points. So if IB is equal to 0, then VBE would be equal to VBB plus V in of T. And if VBE is equal to 0, then IB is equal to VBB plus V in of T divided by RB. At the end, if I run out of time, I'm going to go over 4 p.m. I'll keep recording. If you have to leave at 4, you can feel free to leave at 4. Okay. Which one? To find the points for the load line. Yeah. Load line requires 2 points to find the coordinates. So if it's a line that's plotted on the graph, it must intersect the X and Y axis at some point. The point where it intersects gives us, well, Y equals 0 is the X intercept and X equals 0 is the Y intercept. And so that's what we're doing. And then if, of course, V in of T is 0, then VBE is equal to VBB and IB is VBB over RB. Okay. All right. Okay. So now let's take KVL for the output. KVL for the output, we have minus VCE minus VRC plus VCC is equal to 0. Therefore, I have VCE equals VCC minus ICRC voltage drop. Now to obtain the 2 points, if VCE, sorry, if IC equals 0, then VCE is equal to VCC. If VCE equals 0, then IC equals VCC over RC. Okay. And if we have those points, we'd have a line that would intersect load line there, and we'd have another one here. And then on the next slide, I have an example where we'll talk about how it actually works. All right, any questions so far? All right. Okay, let's look at some values and some example in the example. So we are provided with VCC of 10 volts. It's the same circuit as the previous one. VCC is 10 volts. VBB is 1.6 volts. RB, the base resistor, is 40 kilo ohms. RC is 2 kilo ohms. V in of T is 0.4 sine 2000 pi T. Volts, of course. So from this, I know that my VP is 0.4 volts and my frequency is 2000 hertz. Okay. Oh, sorry, frequency is 1000 hertz. Frequency actually does not matter for the most part. But what we want to know is how far is that input moving. So it's going plus 0.4 and minus 0.4 volts. So V in of T swings between plus 0.4 and minus 0.4, max and minimum values. Right? Everyone remembers fully? So on the images, the load lines are already plotted, but let's hold off on looking at those images just for now. Okay. On the input side, if you want to plot our load lines, we need to obtain the equation from the previous slide. And we're going to write down for the input I/P is just my acronym for input. So input, I have what? IB is equal to VBB plus V in of T over RB. So at the Q point, V in of T is going to be 0, right? Q point means just the values of the voltage and the current without any AC input applied. It's solely due to the DC voltages. So IBQ means just my VBB, V in of T is equal to 0. So 1.6 divided by 40,000 gives me 40 microamps. Does that make sense to everyone? It's an amplifier. So before we apply the AC input, we apply the DC biasing voltages. When we apply the DC biasing voltages, our Q point is fixed in the active region. When it's fixed in the active region, it has current value, it has voltage value. So on the input side, it is VBE and it is IB. Okay, this is without applying any V in. So on the input side, I have this point right here, 40 microamps. Sorry, not that, 40 microamps here, because you're still plotting the load line. And then as the AC input is applied, that Q point is going to shift. Okay, that Q point is going to shift. So the max value for IB is going to be 1.6 plus 0.4. Which gives me a value of 50 microamps. So again, this is solely due to VBB. Okay. V in of T is equal to 0. AC is not yet applied. But now when you apply the AC, my Q point starts shifting. It's moving. And so when input reaches a peak of plus 0.4, IB goes to a peak of 50 microamps. It gives me a second point right there. And then similarly, we find the minimum point. So IB minimum is 1.6 minus 0.4 divided by 40,000. And so now I get a value of 30 microamps, which is this third point right here. Does this make sense? You're applying a DC voltage. When you apply a DC voltage VBB at the base, it establishes a Q point, which means your base current is now fixed. Your base current is fixed at 40 microamps, 40. And then when you apply an AC input on top of your DC biasing voltage, VBB, so now it's VBB plus V in of T, which is what you did in lab 8. Now your Q point shifts. And because it's shifting, your base current is moving. So your base current increases with increasing V in, and it decreases with decreasing V in. So if V in goes to a positive peak, your base current goes from 40 to 50 microamps. When it goes to the negative peak, it now goes from 40 to 30 microamps. Let's take a pause. Does that make sense? What? Yes, right here. It's on the left side. It's very, very tiny, unfortunately, yes. No, so we will calculate these 3 points in the next step. I just want to show how it's actually changing. Okay. All right, so let's find VBE. Since we found current IB, VBE is simply VBB plus Vin. So VBEQ is simply VBB, which means it is 1.6 volts. VBE max means it goes 1.6 plus 0.4, so it goes to 2 volts. And VBE min means it goes from 1.6 to minus 0.4, so 1.2 volts. So we found the current values first. Now we found the voltage values, which are right here at the bottom. And once we find those 3 values, we join our lines. And so we have our 3 load lines. The middle one is solely due to VBB. The other 2 are due to VBB plus Vin and minus Vin, positive peak and negative peak. And as with any load line analysis, the load lines intersect the characteristic, and the point where it intersects the characteristic is our Q point. So this in the middle is our original Q point. When you apply V in, the Q point shifts up and shifts down. Okay. This Q point is due to plus VP, and this one is due to minus VP. So our input waveform is actually shifting. It's something like this, if you will. Okay. Now the coordinates of the Q point are important because that's where our transistor is operating. So we need to obtain the coordinates of those Q points. And the coordinates of those Q points was IB is equal to 15 microamps, 25 microamps, and 35 microamps. Okay. And then VBE is not actually important. It's 0.6 volts to 0.7 volts. Okay, so we have the coordinates of the input current. IB is 15, 25, and 35. And so then we go on the output graph and we plot our load line. So the output load line or coordinates for the output load line, VCE is equal to VCC, so it's simply 10 volts. And then IC is equal to VCC over RC is equal to 10 over 2000. So IC is 5 milliamps. And the 2 points here, VCC is 10 and IC is 5. You plot the load line, and that load line is going to intersect all of the output curves at a single point. But we are only interested in 3. The only 3 points we are interested in is where it intersects 15, 25, and 35. And those points we obtained from here. Okay, so we are looking at seeing how the input is transferred to that output. $15, $25, and $35. Okay. We are almost there, almost done. Okay. So now let's take a look and see what happens if you're sending an input. Now, remember the scales are different. Your IB values are in microamps and your collector current output is milliamps. Okay. It's 1,000 times. All right. Let's say you are sending in your input. Let's draw it this way. And this is your input right here. All right. That's your input waveform, V in of t. Okay, so what happens? At the Q point, when your input current is 25 microamps, what is your output IC? Anyone? Output IC is 2.5, right? When it goes maximum, IC goes max, so you get 3.5. So 2.5, 3.5, and when it goes minimum, you get 1.5. Okay. However, the more IC increases, the more is the voltage drop across RC. So your output VCE decreases with increasing IC, and output VCE increases with decreasing IC. So the corresponding points for VCE, let's draw it out like this. And that's my output. My output VCE is going to look like this. So for maximum current IB, I have the minimum value for VCE. For maximum or minimum value of IB, 15 microamps, I have maximum output VCE, 7. And hence, my output is an inverted amplified version of the input. Your VBE only swings between 0.6 to 0.7. Your input current IB only swings between 15 microamps and 35 microamps versus my output collector current going from 1.5 milliamps to 3.5 milliamps, 100 times. And my output VCE swings between 3 volts and 7 volts. So my output is amplified, but it is also inverted. Plus, it has a DC component or a DC offset to it. If I was to plot this, VCE going this way, this is my DC offset in the output. So there is no way to avoid it. We cannot avoid the inversion, and we cannot avoid the DC offset at the output. Okay, we are past 4 o'clock, but I am available to answer any questions you may have. This derives from the load line, but it requires a lot of steps, so it might get a little complicated and confusing. Take your time to review this, but it will definitely enhance your understanding of how the CE amplifier works. Okay. So we'll end class here today. I'll see you all on Monday. Please review the lecture video and the notes. And then, of course, reach out to me when you have any questions. All right. Have a good weekend. And I'm still around if you have any questions.